So what we have left for you is now we're moving away a little bit from electrostatic or electricity. So that means we're going to move away from Coulomb's law, the potential, the forces, and all this stuff. Now we're going to look at something that sort of like towards like it's like more applications that you can get a little bit closer in your actual experience, right? You might be able to even do your and I don't know, you call it like some kits that you can buy online, and then you can do some electronics and other stuff with it. So it's still business of the capacitors, but we're going to learn a little bit more before we move on to something that we going to do some analysis on circuits. Okay, so we're going to learn about circuits, and we're going to do some analysis. And when we talk about circuits, electric circuits over here, of course, you have already heard this law many, many times. It's Ohm's law. So we're going to sort of like do a quick review of what the Ohm's law is about just one more time. And then we're going to do some simple electric circuits that you use Ohm's law, which will look maybe just exactly like what you did back in the day of like middle schools or high school physics and all this stuff. However, the main focus of our analysis will be this one right here, guys, the Kirchhoff's rules. Okay, so let's see if I can get to that. If I can get to that, I'm good. So this is going to be the goal of today's lecture, is just get to introduce to you what is the Kirchhoff's rule and how to use those rules. Cool. All right. Once you have that rules, you will have a chance to do the analysis of a circuit that is more complicated than the one that you can use only Ohm's law to analyze. Okay. And you will have some examples that I can showcase what kind of utilities that you can get out of Kirchhoff's rules. Sounds good? All right. And I'm telling you, it's the easiest part of the course. I'm pretty sure. All right. I'm pretty sure it's the easiest one, because this one is like, once again, I'm referring this one to the recipe. And this recipe, once again, just like what we introduced to you last time about whenever you have a recipe, even though you don't understand or you don't have the internal understanding of how those ingredients combine, but if you follow the recipe, you're going to get to eat it. So this is exactly it. Even better that there's no calculus. There's nothing. It's all algebra. All right. So at the end, once I sort of like give you the the summary of everything, and if you follow this recipe, it turns out you have an ability to do the Kirchhoff's rules based problems very easily. All right. So that's very cool. All right. And we're going to save the best for last. Well, probably not the best, but at least we're going to save some. Well, we have already seen it, but we're going to have a chance to look at it one last time before we finish our course here, is by solving some differential equation. But that is going to be the business of next time about the RC circuits. Sounds like a good plan? Okay, and I think we're going to call this like the end of our course right here. So that's why this is where we sort of like, get you guys to the end of the road here for the last 2 weeks. So that's why I put like week 10 and 11, stuff like that here, because that's how much I can pretty much squeeze in like a little bit of right, 3 months and a week or so mid lectures. All right, so that's what it's happening, and it's happening again. It's already happened in the past, but this is exactly just like last time. So I cannot go beyond this one. I don't know why. Okay. All right. Okay. Very good. So let's get things started here. So before we move on to that, let's do a quick connection to what we did last time, right? Last time we were talking about capacitor, okay?
Okay.
And the easiest construction of a capacitor is just having a parallel plates, okay? And once you charge those plates by transfer charge from one plate to the other, so one plate will turn positive, the other plate will turn negative, you generate an electric field in between, all right? So that's no big deal. That's what we did last time. And when you use Gauss's law to calculate those fields, get the field to calculate the potential difference. Once you have the potential difference, then you just put into your formula and calculate the capacitance. Okay, so far so good.
Okay.
So that's one is fine. Today, it turns out the space in between that you looked before, it was just a blank space. And you're probably wondering, how can we keep the structure separated like this, having the blank space in between, right? Because we're not gonna like it if these two plates eventually gonna sort of like come down and touch each other. That's not good because you're gonna have charge running around and neutralize everything. So you probably don't like that. So having the just a blank space in between, all right, it may be good in some configuration or something, but in the device that you have seen in a photo before that I showed you last time, the capacitor that you found in your PC computers, in your electric circuit boards and all this stuff, they're not going to have like any blank space in it because it's going to be so hard to use. So what happening was, yeah, instead of having a blank space, you probably want to, you know, sort of like reinforce it with something, right, to make them separated, okay, the positive plate and the negative plate. However, somehow, actually, our physicist or maybe whatever engineer, whatever, they sort of like came with a good sort of like way of utilizing those space, and they are able to enhance the capacitance. So not only just squeeze in something, but they have some special material that once you squeeze it in between, it turns out you can change the capacitance of the capacitor, which you guys know already from last time. It's like, okay, Ajahn, the capacitance depends on the physical constructions of the capacitor. So this probably have the same effect because we discussed last time that, for example, when you have like a touch screen with your finger and without your finger, the capacitance are not the same. Over here must be exactly the same. With and without things in between must give you the different value of the capacitance. But then because sometimes you want a high value of capacitance, but you don't want to change your physical appearance. So this is a very good chance that you can utilize this. So we are going to squeeze in some material in there that allow you to increase your capacitance without changing the dimension of the capacitor. Sounds like a good plan here?
Okay.
Cool. And what kind of material is that? The material that we are talking about is called dielectric material. All right. This material is kind of like, I think you guys are already familiar from maybe chemistry. So you guys look at the H2O, okay? So the water molecule. So what I can draw, probably I can draw this like an O, and we have hydrogen atoms on the side like this, okay? So when you look at the H2O, even though it's a neutral molecules, but you guys knew from chemistry probably that if you talk in terms of like electronegativity, right? Remember that one, yeah? So when you talk about electronegativity, you kind of like, you have a list of the electronegativity among those elements in the periodic tables. And it turns out the oxygen has a higher electronegativity than hydrogen. So what it means is electrons seem to be able to spend more time around oxygen molecules than around hydrogen atoms in the molecules. So that's why in the H2O molecules, turns out the oxygen side of the molecule seems to have a little bit more negative than the hydrogen side. So I can replace this whole shape of the molecule by just a simple, maybe just a representation of this whole thing. Just like, okay, I have like a piece of molecules or a piece of charged particle. And it turns out I can sort of like divide this in half. I can say that the upper half has a more negativity than the bottom one. So I put like a negative side on the top and a positive side in the bottom. So that sounds reasonable here?
Okay.
All right. So with that, we call these molecules has a polarity. There is a polarity. So the polarity of the molecules just saying that it's not perfectly neutral everywhere on the molecules. There are some part of the molecule that is more positive than the other parts. All right. So it has some direction to it. So you can actually assign some sort of like a directions of this positive and negativity along of the molecule, all right, due to the shape of the molecule. So if the molecule is oriented like this, I can probably point something like this. Let's say, hey, if this arrow representing the direction between the negative to positive, then I can put an arrow pointing downward. So everyone knows like the bottom half of this molecule is more positive than the upper half. Does that make sense? All right. So that means every molecules in this material can be represented by using these arrows or this like a capsule-like molecule. So that's what this figure is showing you. Okay. However, in general, when you don't have any restriction on these molecules, so these molecules can pretty much orient it in any direction. That you don't have anything that can force them to point in any direction in particular. So that's why in general, these will pretty much randomly oriented. So you won't have any sort of like net effect due to these orientations because they are random. Okay. However, this is very interesting. Once you apply some external electric fields, guys, what do you think it will happen? Well, of course, again, positive charge will try to move in the direction of the electric field, right? We already learned that from Coulomb's law or whatever the property of the charged particle in the electric field. On the other hand, the negative part or negative charge they're trying to move against the field. Does that make sense? All right. However, these negative and positive charge are part of the molecules. So they cannot just be sort of like torn apart and then, separate them or ionize them. So that's not possible. So the best way that they can do is they just do the rotation. Does that make sense to you? So you can think of this just like a compass. Just like you put a compass under magnetic field. So it's going to point north all the time. Same thing over here, but this is all electric. So what you have over here is that means all these polar molecules will try to align themselves in the direction of the external electric field. Cool. Now, all right. So that's what it is. So the dielectric material is the material that you can think of it like it can respond to the external electric field. And when I say respond, it just means like they're trying to orient the molecules axis. The axis of the molecule is try to line up with the external electric field. Does that make sense? Okay, so they're gonna have like a now sort of like very, very order orientation. So what I can do is I can draw a cartoon version of this. This is a cartoon version of that. So this is what happens. So overall, what will happen is the positive portion of the molecules try to turn to the right, while the negative side of the molecule try to move to the left side of this whole thing against the field. Okay, so the cartoon version goes like this. Now, don't forget that the amount or the numbers of molecules in the material is like a big, crazy number, right? It's like it's huge, Avogadro number or stuff. So we have million of that. So what happening is this. So it turns out, if you look at the positive side of this molecule, it's going to be pretty close to the negative side of the neighboring atoms or neighboring molecules. Does that make sense? Okay. So same thing happens to the positive side of that one. It will be pretty close to the negative side of the neighboring molecules as well. And this whole thing keep going. So overall, if you look inside this dielectric material, inside, you are pretty much looking at the cancellation. So it's sort of like it's a neutral region. This is neutral because you have the same amount of positive and negative. You look at this one, like, this is neutral. You look at this is neutral. So what happens? There are only two parts of this dielectric material that doesn't have any ability to cancel to canceling with their neighboring molecules. It's the side, the negative side on the left. You see that? This area of the dielectric material doesn't have any positive side of the neighboring molecules to cancel with. So it's just like, okay, that's a negative one. It's there. There's no cancellation going on. Same thing with the right side of this one. The positive ends of the right side molecule doesn't have any negative side of the neighboring molecules to cancel with. So all in all, the overall picture goes like this. It's just like you have a negative layer of charged particle, and the right side of this one, you have a positive layer of that. Does that make sense? Is that okay?
Okay.
Sort of going along with me right now. So what you have over here is just like, oh, by having the dielectric material in there and you apply your external electric field, the dielectric material generates something like a parallel plate capacitor by itself. Does that make sense? Because if you look at this dielectric material, the positive layer is on the right, the negative layer is on the left, with each opposite is generating the electric field opposite to the external electric field that point to the right. You guys with me? Okay, so the textbook figure over here is just trying to show you the whole thing over here. So the E naught right there, that was the external electric field. That was the E naught right here. Okay, same thing over here. And the E naught, the E prime over there, that is just the electric field due to the induced. We call it the induced because first it wasn't there, but now it's there because you put external electric fields on it. So they rearrange and generate the electric field internally against the external fields. Cool?
Okay.
All right. So what does it mean is overall effect. You look at this whole chunk over here. This is your capacitor, right? So when you look at the whole chunk over here, your net electric field is smaller because you get cancellation. Yeah, the induced electric field inside your dielectric material points in the opposite direction to the electric field that you put in externally. So you get a net smaller electric field overall. Cool? All right. So what is happening here is, Ajan, now what will happen to the whole thing, right? So now your electric field, let me call it the net one. Oh, my writing is bad. Net. Oh, is smaller. It's reduced. So I'm asking you, hey guys, what will happen to the potential difference? You want to know what is the potential difference here? So what do you think will happen to potential difference? Is it going to increase or decrease, guys? What happened?
Okay.
Very good. Electric field is lower. The field is lower, so the potential is going to be lower too, right? That's hand in hand. And what happened to the C then? Capacitance. From the definition of this, capacitance is just the charge per voltage difference, right? However, you haven't changed anything. The amount of charge on the plate stays the same. You only have now dielectric material on it. So that means by having the delta V decreases, you eventually increases the C. And that's what the consequence of having the dielectric material in between the plates. Isn't that cool? Right, all right, but that's what happening here is showing having the dielectric material show up in the space in between. Induce the electric field against the external field. So you reduce the net overall electric field between the plates. So reducing the electric field between the plates lead you to smaller potential difference at the fixed amount of Q. So that means for the same amount of the charge on the plates, you have a lower potential difference across the plates. And hence, at the end, you get a larger capacitance. And that's how you enhance your capacitance. That's the conclusion.
Okay.
Cool. Now you start to wondering about Jan, to calculate this induced electric field and things like that is going to go like crazy because you saw before we had to use like Gauss's law to do the blah blah blah. The answer is no. No, there's nothing complicated at all. And I'll show you just right now here. So if you look back at this, okay, let me start from this. When you look at this one, okay, everyone now realize that this is just a Gauss's law. The term on the left is just a total flux. The term on the right, that's a Gauss's law saying that the net flux is just a charge enclosed divided by epsilon naught, correct? You don't have to do anything new anymore. Now I'm going to review some secret over here. It's not a secret, actually. I'm going to review something. Why you need the not in your epsilon? Have you ever wondered? Why the constant epsilon need like a subscript not in there? The reason for that is because this is just to signify that this is for a vacuum or a blank. It's just a blank space. So when you say not, mean it's nothing. It's just like nothing. It's the blank space. Okay. But now you want some other material in the way. You don't want to just blank space anymore. So what are you going to do? So let me sort of bring you guys back to this, guys. Yeah, electric. Let me do just a positive charge. All right. So you guys know that around this positive charge particle will generate electric field, right? Here we go. Electric field pointing out. And if you are standing at some point, you can calculate electric field here. It's just going to be that K. Now I'm writing in terms of the 4 pi over epsilon naught. The Q generating the field divided by the distance square if the distance here is R. Cool? Now, here, if I place this charge in water, ooh, I'm just going to place this whole thing in water. Do you think what will happen to the Coulomb's law, guys? Well, Ajahn, well, it's not a blank space anymore, but now it's water. The only thing that you need to change, turns out, instead of using the epsilon for the blank space, you try to figure out, you replace this with the epsilon of water. Does that make sense? Simple as that. That's it. So epsilon naught is just, think of it like it's a constant for that space that is, which is blank at that point. So now if you want to place any charge in other material, you just replace the epsilon naught with the epsilon of that material and you are done. So that means if you would like to apply Gauss's law where the environment is not just a blank space anymore, what you just need to do is just, okay, done, forget about this naught here. You find epsilon of that material. So your Gauss's law would look something like this. See, just epsilon of that material, right? However, things get even easier. I can define the value of epsilon by comparing the value relative to the epsilon naught. So what I'm going to do is this. I'm just defining some constant for that material, and that will just tell you what would be the value of the epsilon of that material by having that factor in front of it. We call that factor the dielectric constant. There you go, guys.
Okay.
Okay, my drawing is really bad, but it's here. Sorry. That kappa, or some textbook, they might just use K, doesn't matter. But whatever the K or the kappa here, that is called the dielectric constant for that material. So you just, if you only know the dielectric constant of that material, you just multiply that to the epsilon naught, that will bring you to the epsilon of that material. So for this particular example that I'm showing you for the case of water over here, all I need to look up is just what is the K or the kappa, the dielectric constant for the water. And I just multiply that in and I'm done. Cool? You guys almost done. See how easy it is? Yeah, I hope you are seeing what I'm saying over here. So this table shows you some value of some, common materials over here, the dielectric constants for some common material. Look at this one. The air is not perfectly blank. So it's not epsilon naught exactly. It's 1 a little bit. So as you can see, the dielectric constant for air is 1 point something. Okay. Now look at this. Paper. So paper has something there. Oh, it's about 3.5. Next, what else they'll be familiar with? Water is huge. We know that because we know that water is very polar. It's highly polar. It's polar, polarized molecules, right? Water, yeah, it's very is very polar there. So there is a high polarity for water. Okay, what else? There are like super huge, like big value of the dielectric constant made out of some ceramic. So you have like some mixture of titanium, maybe some, some weird, like, I don't know, aluminum, silicon, or the stuff like that to make some super high value of dielectric constants. So why do we need this? Now you start to see why. Remember the formula for the the formula for the capacitance of the parallel plate capacitor from last lecture? It's epsilon naught A over D, right? Remember this one? The keyboard. Remember the keyboard, right? So, right, the capacitance depends on the cross-sectional area of the plate and the distance between the plates, right? But now you will see what I'm seeing here, guys. It's epsilon naught. So that means if now you squeeze in some dielectric material between those plates, all you need to do is just replace this with the epsilon of that material. So I'm going to say C with dielectric constant is going to be epsilon A over D. And I'm done.
Okay.
And because you said that you can figure out the epsilon by just multiply by the dielectric constant to the original epsilon naught divided by D. You see, but this is your original capacitance without any dielectric material. So that means by squeezing your dielectric material with dielectric constant kappa, you can change your original capacitance by that kappa times. So the kappa will give you the multiplier. It will give you how many times bigger than the just a blank plate that you can get. If you squeeze in the paper in between, you can increase the capacitance by 3.5 times. If you put water in between, which you shouldn't do in general, but if you want to put water in there, which is, you're going to short them all, but anyway, so if you put water in between, it's possible if you do chemistry, if you do like chemical reaction and other stuff, or you do some like photovoltaic and all the stuff, there are some liquids there, you have charged plate left and right, that's also possible. But for us, it probably doesn't make sense to just throw in some water into your blank parallel plate capacitor. So that won't be something that you want to do. But anyway, if you want to do it, it will increase your capacitance by 80 times. And now you understand why. So that means if you squeeze in some crazy material there that you already engineer for it with the same dimension of your original capacitor, you can improve the value of the capacitance by hundreds times. That's what it is.
Okay.
Cool. And as you can see, simple.
Okay.
So all you have to do is just multiply by the dielectric constant and you're done. So that means the formula that you've seen before, you just have the kappa factor in front of the epsilon naught. This is the one that I'm going to show up. I'm going to put it in the final exam. See, whatever the formula that you got, you just put the kappa on it. That's it, guys. Okay. So that is so good. All right. So let's take a look and see what will happen in terms of the question that we can analyze. You have a parallel plate air-filled capacitor has a capacitance of 50 picofarad. So pico over here is 10 to the negative 12. Okay. So now if each of its plates has an area of given to 0.25 square meter, what is the separation? It's air-fill. So air-fill, we assume that just a blank space, right? So don't need to worry about anything. You can assume that the kappa of this one is just 1. Okay. So you can refer to, let me call this like air. It's just going to be epsilon naught A over D. This is just a direct formula to calculate the capacitance of a parallel plate capacitor. So over here, you just plug in the number epsilon naught. You can look it up. The area 0.25 square meter is already in the square meter. Very good. The separation, this is what you want. And somehow they already gave you that the C of this one is 50 picofarad. So from here, you should be able to figure out the D. Okay, not, yeah, just put that. There you go. So you're done. Okay, so that's not bad.
Okay.
Now, part B, if somehow the region between plates is now filled with a material having the dielectric constant kappa 5.6, what is the capacitance? So part B is going to be simple. So let me call it a C prime, the new value of it. It's just going to be kappa of the C with the A in between. So my answer will be 5.6 times of 50 picofarad. And I'm done. That's it, guys.
Okay.
Is that too easy? It is that easy. All right. So love this one, right? There's no complication to it, even though the underlying properties of the dielectric material is very interesting, but the final outcome and the kind of things that you need to calculate is super easy, all right? By going through dielectric constants. Yeah, try again, guys. Try this one. So an air-filled parallel plates capacitor has a capacitance of 1.3 picofarad. The separation of the plates is double. All right, this one is very good. All right, I like this one because I think this is pretty close to the level that I will show up in the exam. So you don't have to sort of like doing real numerical calculations. You don't really need calculators, but you just do some analysis here. And now the wax is inserted between them. Okay, so that means you double the separation. So you sort of like spread them out a little bit, and then you squeeze the wax in between. It turns out your new capacitance turns out to be 2.6. So you double your capacitance. What is the dielectric constant of the wax? You want to give it a shot here, guys? Woo.
Okay.
Too long, eh? All right, guys, give it a shot for this one. So this one is, once again, it's fall into the category of comparing between two scenarios. So the only thing that I love to do all the time, since we doing some thermodynamics, gas law or whatever, was just like doing like the condition number 1 and condition number 2 and compare. So let me do this. So let me start with the air field. Let me call air field the first condition here. It's going to be epsilon naught A1 over D1. You guys with me? Whatever that's following the first condition, I just put the subscript 1 onto it. And then I do, after you do the changes and everything, you get the new value, which is C2. So it's going to be now, it's going to be new epsilon because now you don't have any epsilon, the original anymore. So let me call it the epsilon of wax times the area. You could be the new area. Let me put it like A2. And then you can put like D2 if you want to change your separation. And now the way that you compare these two is very simple. You just divide them. So what I can do is I can take like equation number 2 divided by equation number 1. If I call this equation number 1 and number 2 here, right? So you call it the mu C over the OC is going to be, and now I'm just going to pair up term by term of the same parameter. So I can call it the epsilon wax over epsilon naught. That's one pair. And now you can do area against the area, and then the distance between plates against the distance between plates between two conditions consecutively. Yeah, cool. All right, now because for this particular problem, you don't change any area, so these two just cancel out, just turns into 1. You said that you doubled the separation, so that means this ratio will turn into 1/2. You guys with me? Because D2 must be twice D1. So you could get the last ratio to be 1/2. Now the first one, you guys know that now your epsilon of the wax is just going to be the dielectric constant of the wax multiplied by epsilon naught. Cool. So that means the epsilon naught eventually cancel and you only get the kappa of the wax left on the right side. Now on the left-hand side, you have the mu and the OC. The new one is 2.6. The old one is 1.3. So this means the ratio on the left is just 2. So now what I got over here is just this equation, and you can solve for the kappa of the wax is just 4. That is your dielectric constant of the wax. Yeah, not bad. See, so love it. So this kind of problem is not bad at all. And then now you understand how can we deal with this kind of thing. So for this particular one, I leave you as a DIY. Okay, because this one is asking you about the coaxial cable. So it's a coax cable. And this one is going along with the question that I would like to post in our final exam about the cylindrical capacitors. Yeah, so that means you need that value. I mean, need that relationship about finding out what is the value of the cylindrical capacitor, cylindrical capacitance to use to calculate something like this. Okay, all right. So this one sort of like give you a clue of what kind of question will show up in the final. All right, cool. All right, nice. So that's wrap up the topics of capacitor and capacitors. Okay, now what we want before the break. Okay, I just want to move on and just introduce to you before the break, just to remind you what we're going to learn next is now about the current. So that means now we are going to allow those charges to move now. So what we have done up to this point was just static. Charges are standing still. You find in the field, you're finding the electric flux, you're finding electric potential, blah, blah, blah. Everything is just stationary. But now we want those charges to move. Okay, they are going to travel. So the easiest way to describe something that is moving is just talking about the rate of movement. So that's why we introduced the rate that the charge flows through any cross-sectional area. So of course, it's just like you think of it like you have a door. You open up the door and let the charge move, and then you just have to check like how many charges has been traveling through the door, and you just count them. Once you count them, you know that each charge carry how much charge. You just find out what is the total amount of charge that going through that door. And that door has a cross-sectional area somehow. But the flow, it turns out, is just the rate of the flow. So every time that you want to talk about the flow, it's in general is per time. It's per unit time. Okay. So that means it's going to be defined as the amount of charge that flow through per second. So that's why your current is being defined as charge per unit time. And because we know the unit of charge is coulomb, the unit of time is in second, we have a special name for this one. It's called ampere. So everyone probably familiar with that. So like how many amp, this is the one. Okay, it's an ampere. It's just the coulomb per second. Okay. And just like once again, it's unfortunate that we define the direction of the current flow depends on the positive charge, even though in real life, most of the stuff is coming from the movement of the electrons. So that's why if you are talking about the movement of negatively charged particles, the traveling direction of those negatively charged particles has to be in the opposite direction to the direction of the currents. Okay, so this is just a side note, just saying that we define everything according to positive charge. Okay, cool. All right, so with that, then we have an Ohm's law, okay, which is the law that is not a law at all. So this is not like a super like, I don't know how to say it. It's not like super duper law like sigma F equal to MA, or it's like KQ over R squared, like Coulomb's law. I don't know why this gets praised to be like a law. To me, it's just like a relationship, or it even like, I don't know, it's like just like a experimental observation, or I don't know, it's like, anyway, but now it's already a law, so let's call it a law. So Ohm's law says, this law saying that if you somehow apply the potential difference across the material, and that material allow the charge to flow, the flow of the charge under the current flow can be calculated, okay, or the change of the potential and the current flow are linearly depend on each other. So what they're saying over here is the potential difference, which is once again, just to confirm that it's the same thing as a delta V, is proportional to the amount of flow that you're going to get. Okay, that's simple. Okay. And you can turn this into an equation once again by introducing a constant to it. There you go. And that constant there is there is an interpretation for that, because if I rearrange this one and sort of like set the R on one side and move everything else to the left, to the other side, it turns out the amount of flow that you get is inversely proportional to that R, the constant that you introduced there. So that's why it seems like the bigger the R, the smaller the flow. So that's why we're going to name this R the resistance, because it seems like the flow sort of like hits the R. The bigger the R, the smaller the flow. So it's sort of resisting each other. Okay. And this is what it is. So it depends on what you have seen before. You might see you might have seen Ohm's law in terms of V equal to IR, could be, or you probably have seen like I equal to V over R. That's wherever that is. These are all Ohm's law. Okay. So in essence, Ohm's law is just saying that the amount of current flow is linearly proportional to the potential difference across. That's Ohm's law. Okay. But the reason I say it's not, it shouldn't be like law, because a lot of material does not follow this guideline at all. There's so many material that you apply voltage across, the current flow is not linearly depending on this, right? So many things. Okay. But anyway, just so you know. All right. So the units of the units of resistance is going to be simple, because it's the ratio between the potential difference, which is in volts, and divided by current that we just define in ampere. So it's a volt per amp. We have another name for it. We call it ohms for this one. Okay. So that's ohms. So that's Ohm's law. And we use that as a unit for resistance. Okay. Cool. So with that in mind, so what we can draw the conclusion out of this is, well, อาจารย์, once we know the relationship between the current flow and the potential difference, but we already learned that the potential is just the connections, or another way of talking about energy. Potential is just energy per unit charge. Oh, อาจารย์. So that means if you want to go back to energy, you should be able to do it very easily, just like what we had before. Energy is just the amount of charge multiplied by the potential difference, right? So that's going to be super duper easy now. So what happened if you want to talk about the energy flow? Even though you want to talk about energy, like just energy, that is fine too. But the reason that we want the flow, because the current is already flowing. So we probably want to talk about the energy that goes along with that flow. So let's talk about the energy flow. So think about it. But okay, Ajahn, if it's flow, mean it's per unit time. So if I talk about the energy change per unit time, oh, that is the definition of power. Energy per time. However, we already learned that the potential energy is just the amount of charge multiplied by the potential difference. So far, so good. Okay, but then if you pair this charge with the time, I'm right down over here already. So if you pair the charge with the time, that is the definition of the current. So that's why you get a very simple relationship, allow you to calculate the power of any flow of the current through any potential difference. It's just a product between them. I times V, and you are done. Cool?
Okay.
All right. And now combine this with Ohm's law, V equal to IR, R equal to V over I, or whatever. You can change V equal to IR and you can write it down as I square R, or you can write I equal to V over R. You can turn this into V square over R. Up to you. Depends on the information that you have. That allow you to calculate the power. And because the power is in the unit of watts, so there's no doubt you're using all the time. When you have the light bulb, you have the light bulb with so many wattage. And the watt, that is just the power that is being used by that light bulb. So for example, if you have a light bulb that is marked with 2 watts, when you apply 1.5 volts across it. So from now on, you are able to find out what is the resistance inside that bulb. Yeah. So you say, oh, Ajahn, this is power. This is V. You want R. You probably pick this relationship over here. So you just say R equal to V squared over P. And then you just take the numbers over there, square them, divided by the power. You get the resistance in that light bulb. and you are done.
Okay.
Okay, so hopefully by knowing this, you can go back and look at your charger, the adapter that you have, like a supercharge, super fast charge or whatever. In the specification, it will have to tell you what is the amount of current flow, like maybe like 2 amps, 1.5 amps, and what is going to be the voltage across. It could be like 5 volts, whatever. And then when you do a supercharge, it doesn't have to be supercharged. When you do the charging, then you just multiply those two numbers. It will give you the amount of watts for that adapter. That's already there. Okay, so that's an easy relationship between the I and the V. Cool. All right, guys. So let's take a stop over here. Yeah, so like a quick break. And after the break, we'll start dive into the sort of like the circuits analysis. Okay. All right, guys. Take 10 minutes break here.
Okay.
So what you're seeing over here in this slide is just the conclusion about the maybe just some properties of material. I'm sorry, the property of the electrical energy that we just discussed, and a little bit of terminology that we're going to use in the circuits. Okay, so what you're seeing over here is the point of having the resistor in your whatever that we're going to name the circuit is it's the portion of the circuit that take away the energy. So that's what it is. So what I'm saying over here is the electrical energy, the one that you calculate, the U, the change of the energy or the stuff. Once you get into the resistor, it's the part that actually take away the energy out of your circuit, and mostly is in the form of thermal energy. So that's why the things that get hot in your circuits, in your appliances and all electrical devices, is because of there are resistance in your circuits. Okay, all right, and whatever that presents you with the resistance in the circuit, you can always name those resistors. It doesn't have to be like an actual resisting device that's used in electronics or whatever. Anything that pretty much presents some resistance into your circuit, you can represent them as a resistor in your circuit. Okay, does that make sense? So that's why in general, anything that use up your energy, TV, radio, whatever, rice cooker, refrigerator, you can represent them as a resistor, right? As like a representative of that. Okay, because they generate heat and they use up some energy. Okay, so that means if you would like to maintain the current to flow through your devices or whatever inside your circuits, you must maintain a constant current by having an energy source, right? Because those resistance in the circuits will take away the energy. For you to be able to supply the current flow constantly, you have to keep supplying the energy to it. Does that make sense? All right. So that's why you need some energy source. And the way that you can supply that energy source, you can imagine that is your battery. Does that make sense? So your battery over there, that is the parts of the device that allow you to supply energy to the circuits that you use. Okay, so that's your energy source. Okay, and the way that you can sort of like talk about that one, you can name it, it's give the circuit some electromotive force. I mean, the concept of force is not like a Newtonian force here, but it's just back in the day, it seems like this source of energy can push the current through the circuit. So the feeling of push is the same feeling as you supply some force to something. Yeah. So that name still stick around until today. So you have some electromotive. So it's force that can move the electron or something like that. Yeah. So that's the idea. Okay. So you can call them shortly, it's called EMF. Okay. Now you can have like a symbol for that. Usually you can use like E, or you can use a delta V, doesn't matter, because the source of the energy must be the source that can supply the potential difference. So when I say supply the potential difference, it will be clear in a little bit. But the idea is that it's called a pump. Okay, and I'm gonna give you some connection. What does it mean by a pump in the circuits in when you see the whole diagram of the whole thing. Okay, so and everything that we have learned, so the source of the energy, electromotive force, or the EMF and everything, is just nothing more than just the potential difference that you represent inside your circuit, okay, and allow the charge to flow. Okay, so what I'm saying over here is now you can imagine the whole flow of the current inside some actual circuits. You can use a simple diagram just like this. Okay, I think you probably have seen this already, but let's go through this one quickly. So on the left, you might have this symbol over here, or sometimes they might have the symbol that look like this. I think you're familiar with this. Okay, so the longer side over here, that's represent the positive ends of your battery or your source, and the short side of this one, that's called the negative side of it. Okay, so when you have positive and negative like this is a source that give you the electromotive force. But because we now know this is nothing different than just introducing the potential energy across. So that means what you have over here is you introduce the positive voltage or positive potential on the upper side, and you have a negative or lower potential on the bottom side. And because we know the positive charge will roll downhill, you go from higher place to a lower place. So that means if you are considering any positive charge inside the wire, so the straight segments in this figure diagram over here, those straight segments representing a wire, a conducting wire without any resistance. So that means if you have a charge that can travel inside this wire, it will try to roll downhill. So it means you're going to have a flow in this particular direction here. If you look at the upper portion of this diagram, it's left to right, and it's going to keep flowing downhill, downhill until you reach the end of the terminal here. Does that make sense? Okay, so that's why introducing your electromotive force through the source allow the current to flow. Okay, you push the current. But when you say you push the current, it's just that you think about it, it's like you lift the current to a higher place and you just let it ride. Does that make sense? So that, okay, I'm just gonna bring you up. You think of it like you're going to like a theme park or something like that, right? And then you go high and high, or maybe a water park or something, and then you walk up the stair, and then you just do the slider down to the bottom. That's what exactly the battery is doing. Even though in the water park you have to walk up yourself. But let's say you have some elevator that can just lift you up, and once you're at the top, you just like play the whole thing, do the slider and everything down to the bottom, and then you walk up, and then you go up the elevator again. Does that make sense? So your elevator that take you up to a higher altitude is going to be the same thing as the battery that is trying to bring the charge from the low potential to a higher potential there. And once you higher potential, you just rate it right. It's fall downhill, it's roll downhill. So you generate a current over here. Okay. However, along the way, you will encounter some resistance. So that means, all right, think of it like a friction, right? So when you're sliding down, you're losing some energy, you're getting slower, or the stuff, the things that your energy is being lost along the way. And that is a resistance that gets into the way here. And you're representing as a zigzag configuration over here. That's a zigzag. This is a notation or the symbol for a resistor inside your circuits. Okay, and that's it. This is the simple form of circuit. You have the source, you have the resistance, and you have a current flow. Okay, and by having this diagram so simple like this, you can calculate the potential difference using the Ohm's law. That's it. V equal to IR or I equal to V over R, up to you. And that delta V that now we know is the electromotive force. Okay, that's done. All right. Now, this is what's happening here. If you really have a resistor, okay, but in reality, this resistor doesn't need to be like a resistor that you use like in the shape like this. It could be your light bulb. It could be your, like I said, your smartphone. It could be your TV, display, PC, computer, whatever. Anything that takes energy out of your source that can be representing as a resistor. Cool?
Okay.
All right. Now, so what you have over here is when you actually doing it, okay, the picture that I just told you about is the same thing as this. Now let's consider again what happened if you have more than one resistor in your circuit. So over here, now you have the source down here. So follow me a little bit here. I know you guys, some of you probably have seen this before, and this is going to be like a simple to you. But for those of you who haven't done this, so think of it like this. You have a source that can generate a potential difference of E. Yeah, that's an EMF. Now you lift the whole thing up high, or you can think of it like, hey, you provide some potential E to the charge inside your circuit. So the charge is ready to roll downhill, right? Ready to roll. So it's going to roll downhill. So that's give you current flow. But now once you hit your resistance over here, it will take away some energy. Now my question is, how much? How much energy being taken away by passing through the first resistor, having the resistance R1? What do you think, guys? So the thing is, Ajahn, there is a current flow, there is a resistance, we have Ohm's law. Delta V equal to IR. Yeah, that's our Ohm's law. And once again, just want to emphasize, sometimes you don't want to write down the delta anymore. You just drop that delta. So the meaning are the same. So that means every time that you have a current flowing through any resistance, you will always be able to calculate the potential across all the time. Does that make sense? So now, once you know the potential across, that is the change of the potential difference, right? So that means I can say that going from here to there, you're going to face with the reduction or the change of the potential by V1, let's say. But V1 can be calculated very easily. Just say, but Ajahn, it's just IR1. Why not? Oh, from Ohm's law. Okay. Now keep going. So once you travel, you mean the charge. So when the charge keep traveling, now it faces the next R, there is another resistor waiting. So it's now R2. But then because the current flow does not change. Why the I does not change? The reason is because, don't forget, the current is just the charge that is flowing per unit time. Think of this just like a water flow. If you bring in the water a liter per second, that's the rate of flow, right? Liter per second. Every second you must have a liter of water. It cannot get away with anywhere. I mean, this is like a closed loop. So that water stay inside the circuit. So same thing over here. This is not a water flow. It's just an electric flow. So that means those electric charge that is flowing per unit second has to go through the whole thing without any changing. So that means the current flow must be the same for the whole circuit over here. Okay, cool. So what you have here is now you still have the current flow. Now the things that is changed is just the new resistance R2. But the thing is, Ajahn, every time that we have a current flow through any resistor that having a resistance, you can figure out the potential difference by taking the product between I and R. So what I can say is, so Ajahn, you're going through the R2, your potential difference across is just simply IR2. Is that easy? Cool?
Okay.
And that's it, guys. So once you have this, there's nothing else on the way. You can just complete the whole loop here. Keep going. Now you are down to the negative side of this one, and you get up in the elevator. Let the battery bring you up, increase your potential again. So once you show up on the left-hand side, then now you're at the higher level, and then you just ride the slider downhill again. Does that make sense now? I hope. Okay, so having the circuits in front of you like this is nothing more than it's just a conservation of energy. You pump the energy by this much. But on the way here, there is a V1 and there is a V2. What else can it be, Ajahn? V1 plus V2 must be the same as the original energy that you receive from the pump, right? Because it's, once again, it's mgh. You bring it up, but when you come down to the floor, and then somebody pick it up again to this original place, you come back to the original position one more time because we're talking about the potential energy, which is path independent. So every time that you come back here, waiting for the next ride, the energy come back to the original position. So that's why the energy that you lose along the way must be exactly the same as the energy that you supply initially. Cool?
Okay.
All right. So this is just how you utilize your Ohm's laws, and you just put them in the circuit and combine this with the conservation of energy. So you start with the pump of this much. So you give your charge this much energy, but once it fails first resistor, then you lose V1 of the energy. When you face the second resistor, you lose another V2 of energy, and now you lose everything. You come down to the ground level. And then if you want to get another ride, you get into the battery, pick up some energy, you get another pump over here, and now you ride again. Cool? All right. I don't know if my analogy works or not, but I hope you understand how this sort of like the internal mechanics of it's not even like actual mechanics, but mechanism that allow you to understand the electric circuits goes like this. Okay, so that conclude the whole thing is if you have more than just two, you can have tons of resistor in your circuit. If those resistors are connected in the same manner, we call these connections a series connection because they are connected back to back. So you can have a R1, R2, now you can have R3, R4, whatever, as long as they're coming in line, in series like this. The concept stays the same is the potential across this one is going to be IR1, potential across this one going to be IR2, potential across over and this is going to be IR3. So the thing is, the original pump, the energy that you receive must be the same as the energy that you sort of like release on each resistor. So it's going to be V1, V2, V3, sum them up. But then each value is just IR1, IR2, IR3. Now you have a common factor of I. You can put it out. And then you can rearrange this term, make it look like Ohm's law again. So the currents flow in your circuit can be calculated by just E over the sum of the R. And that's why I think this is what you did back in the high school physics. You can wrap this R1 plus R2 plus R3 and call this just a single R of an equivalent value. So that means you can wrap this whole three resistors into a single resistor, which have the equivalent resistance of the sum of those three resistance. Cool? All right, so this is a way that you can wrap a series of resistors into one equivalent resistance. And that value of that resistance is just R1 plus R2 plus R3. If you have more, just keep summing them up. Cool? All right. However, there are complications. Well, Ajahn, if I don't want to go them in series, I don't want to connect them in like, back to back. So we have another way. We call this resistor in parallel. So instead of having them connected back to back, you have like a single pipe. Okay, you have like single line that the current has to go through. Now you have a junction. So once you have a wire and then you split the wire into two ways like this, now you have a little bit of problem because the current has to be conserved, right? When I say conserve, mean if you come in with the current I, but now you have two ways, somehow, you have to split. So if the current flow in the wire number one is I1 and the other wire is I2, then you know that the sum of the two must be equal to the original. So this one is no doubt because it must be come from the actual charge traveling. Okay, so this one is fine. Now the complication is not a complication, but things that actually happen is this. Because you connecting like this, so it means R1 and R2 are sharing the terminals. Does that make sense to you?
Okay.
Yeah, so it means the left terminal of R1 and R2 are joined together. The right terminals of R1 and R2 are joined together over here. So we call this configuration a parallel connections. However, the calculation is simple. Because they're sharing the terminal, the potential across those R's must be the same, right? Remember, it's path independent. So you can call this like a path number one. So this could be like a path 1 and this could be the path number 2. But it doesn't matter because potential difference stays exactly the same. So what I'm saying over here is it means I can calculate the current flow through the path number 1 using Ohm's law again. So I can say I1 is just delta V over R1. That's from Ohm's law. And I2 is going to be the same delta V because they're sharing the same terminals over R2. See that? That's how simple it is. And then I can plug this I1 and I2, sum them up. The sum of the two must be equal to the original before the junction. Okay, plug it in. Okay, let me write it here. Yeah. So the total I is going to be potential difference over R1 plus potential difference over R2. But then when you look at this one, Majan, that junction AB over there connected to the source. Woo. Cool.
Okay.
So that means the delta V that we are seeing over here is just the electromotive force from the source. So you can actually represent this one as the source electromotive force. Why not? And they are just a common factor. So I can pull that E out and see in the brackets what you have is the reciprocal sum is 1 over R plus 1 over R plus 1 over R. So you can also name this one as like, a net or whatever, the equivalence resistance one more time. You just call the whole bracket 1 over R equivalence. And that's why you probably have seen this formula before. Whenever you have resistors connected in parallel, you can figure out the equivalence resistance. That means you're going to wrap everything into a single resistor by taking the reciprocal sum. Cool. All right. So that's something that you probably have seen before, but my focus is on the property of the current flow and about the junction and about the connections, series or parallel. Those are important stuff. And the most important thing is what we have been doing over here is just Ohm's law. V equal to IR. That's all we're using. I don't know. We just flip things around. If you want to find a current, take the V over R. If you want potential, just take the I times the R. It's just going, around within just these 3 parameters in Ohm's laws here. Okay. So with this techniques, with this equivalent resistance, you can now figure out a way that you can try to find, current flow in the circuit that have like multiple resistor in the circuit. So the way that you can do that is just reduce the whole complexity of the circuits down into like a single R. And then you use a simple Ohm's law to calculate the current flow. Does that make sense? So let me show you what I'm talking about by just showing you just this one. The reason I just want to show you just this one because this is not what I want you to do. Some of you, maybe more than half of students in classes here in this course already have done this before. And it seems to me like, okay, if you want to have to redo this whole thing one more time, it won't take you far enough for college level physics. So I'm just going to show you this one. And I think this is enough for you to see how finding out the equivalent resistance allow you to calculate the current flow. Okay, look at this. So they say find the equivalent resistance between point A and point B. And if you read part B, it will be clear. If the potential difference across point A and B is 34, so it's just like if I connect this A and B terminal with a battery that give you 34 volts potential difference across. Yeah, same idea. They just want to know calculate the current in each resistor. So let me show you just this. I want to show you how to calculate the current flow in this circuit over here. Okay, so to calculate this one, the end point or the end game of this whole thing, for those of you that haven't done this before, what you really need at the end is just this. That's the whole purpose of this whole equivalent resistance calculation. So this is it. This is your final results that you really want to get to. So if you can find the equivalent resistance, which is single resistor in the circuit, then from here, you can figure out the current flow by just saying I equal to 34 over R equivalent, right? And you will be done.
Okay.
Okay, so that's why finding out the R equivalent will be the only thing that you need here. So look at this, Bojan. Not bad. I can see that these two are connected in parallel because they're sharing the terminal. Okay, so what I can do is I can just wrap that one down first. So it's gonna look like this. 4 ohms. I'm gonna wrap that one down into a single one and followed by 9 ohms. So let me write this one down. It's 4 ohms here and it's 9 ohm on the right. And in the middle, I want something here. Okay, what is this? So what I'm saying over here is this is, let me call this R equivalence. But because the original one are connected in parallel, so what I can do is just saying R equivalent must be calculated through the reciprocal sum. Cool? So from here, I have to do the flip-flop a little bit, but what I'm getting is going to be 70 over 17. And that's it. That's what you got there. It's 70 over 17. Cool? And now look further. These three are now connected in series, back to back. So that means now I can combine them into a single one. And let me name this one R equivalent prime, the next one. Okay, but because these are equivalent prime coming from three that are connected in series, so I can just say it's going to be 4 ohms, the first one, plus 70 over 17 that we just got, and then plus 9. And that's it, guys. That's your R equivalent prime. And this is what you need just right here. So to be exactly the same, I have to call this R equivalent prime. And then this one prime as well. And you are done.
Okay.
Isn't that cool? Okay. So what this one is showing is this is the way that you use Ohm's law to analyze the currents flow in the circuits. Okay. And if you want to go back and asking what is, they actually asking you to find the current in each resistor. So that's easy now. So now you know the current is given to be this equation, right? So this means you can calculate the current. So the current will flow through this. So that current, the full amount of current will go through 4 ohms. But the hardest part of this one is they're going to have to split here, up and down, right? So how much are they going to split? Do you know? I think maybe this is the hardest one for those of you who haven't done this before. But the idea is still simple, guys. Come back here. So what you looking at here, there are a couple ways that you can do this. You can just say, well, John, if I really want to know, I can call this I1. I can call the bottom one I2. Remember the condition that we have whenever you have a parallel connection, I1 times 7 must be equal to I2 times 10 because they are sharing the same potential difference. They're sharing the terminals. However, you already knew I1 plus I2 can be nothing more than just the original I. See, you have two equations, 1 and 2. So you should be able to calculate I1 and I2, and that allow you to figure out amount of the current flow on each resistor. However, after that, once they have already gone through these two in parallel, they're going to recombine again here. So the current that flow out is going to be the full I again that is going through the 9 ohms resistor. And everything fall down to the floor, get to the negative side of this one, get elevator, up the elevator to the positive side, and let it roll again. Cool?
Okay.
That's the conclusion, all right? If you want to practice, I have another exercise for you to try, okay? So don't forget to try this one just for fun. When I say just for fun, I sort of like guarantee you in the sense that I'm not going to ask you this particular type of question in the final. For those of you that have done like maybe like weird shapes of resistor in connections, like maybe it in the shape of a unicorn or in the shape of like maybe, you know, like a stars or crazy stuff. We don't do that anymore, okay? But this is a good exercise for you to sort of like understand what does it mean by the serial connections, parallel connections, and what are the current flow and what are the potential across each resistors on and on. So those are good. So what's my point today? My point is this. We want to get to the Kirchhoff's rule. which allow you to do something more, but still simple. Look at this, right? This is easy. Even though you have two batteries on here, but it's still all right, a little bit more complicated, but not too bad because you have a single circuit. Everything is still in a single loop. Everything is fine. The current flow in here is pretty much contained. But if I ask you this, guys, okay, forget about this whole process first. I just want to show you this. Can you do this? So the question is, Ajan, now we have a problem here because all those resistors that I'm seeing, they are not connected either in series or in parallel whatsoever. They're like, I don't know, all over the place. You cannot find equivalent resistor anymore, right? You don't know what to do. I mean, crazy. How are we going to be able to solve this kind of circuits? How can you tell which part of the circuit, how much the current is flowing? And here comes the way to solve this one. We're going to use Kirchhoff's rules. The reason I say simple because there are only two rules here. It's called junction rule and it's called loop rule. But the concept is simple. Start with the junction rule. Anytime that you see a junction, we have already seen this a couple of exercises back. The current must be conserved because it came from the actual charge flowing, right? So when the current is conserved, it means in must be equal to out. There's nowhere else to go. So the junction rule just saying that the current total that's coming in must be the same as the current total that's flowing out from that junction. See, that's how simple it is, junction rule. The loop rule is equally simple because we already learned about the potential difference. And when we talk about a loop means you come back to the original position. Then we love the loop. We go up and then you come back down. No potential difference because you are at your starting point right here. So that means you can loop anywhere you want to go as a loop. You can loop around the world, whatever. But once you complete the whole loop, that means if that loop is closed, okay, your net potential difference that you have gone through all those stuff along the loop must sum up to zero. Isn't that simple? Okay. All right. It sounds simple, of course, but the easiest way is just to look at it. How are you going to do it? All right, guys, stick with me here. It's going to be fun, but it's going to be easy. So it turns out I can classify all the cases that you're going to face in this business by just only 4 cases on the left. And look at this, how simple it is, guys. All right, stick with me here, almost done. If you have a portion of the circuit that look like this, and your current is flowing from A to B, okay? You're going from A to B. I'm asking what is the potential difference from A to B? What is delta V? So it's in what is VB minus VA, you guys? But Ajahn, this is easy because it's Ohm's law. V equal to IR. So I'm just say I, if that resistance is R. That's it. The only thing that come into sort of like into this play over here is the current flow from A to B. It means this must be high V. This must be low. Right? Current flow from high to low. Yeah. So that means you're going from A to B, you take VB minus VA, you must have a negative value at the end. You're going to a lower potential. Does that make sense?
Okay.
Okay, try again, guys, over here. If the situation reversed, the current flow backward. When the current flow backward, it means now potential on the B is high. And the potential at A is low. So VB minus VA is still IR anyway. It's Ohm's law. There's nothing else. Current going through resistor with the resistance R giving the potential across IR. But now it's positive because you're going from, I mean, it's A to B, but you are facing the current that is flowing backward. So you're going toward the higher potential. Does that make sense? Not bad. All right. So this is 2 cases done. Now the other 2 here. If you are facing like a source of energy, you have a battery, And I'm asking you about, hey, what is VA minus VB minus VA, guys? Well, Ajan, your B terminal is already connected to the positive ends of your battery, right? And your A terminal is already connected to the negative ends of this one. So no doubt, the potential difference across must be positive, whatever electromotive force E that you are having with that battery. You're done, right? On the other hand, if the situation reversed, the B is connected to the negative end, the A connected to the positive ends of your battery, VB minus VA is going to be just a negative E. Guys, that's it. That's all you need. So you already, looking at these four cases, you already know how to calculate the potential difference. These are all delta V. So all you have to do is you just keep checking out the delta V along your loop. And if you are able to close a loop, the sum of this whole delta V must be 0. Cool?
Okay.
That's how easy it is. So let me show you how quickly this can be done, guys. So what I'm going to do is this. Okay. We're going to practice this once, and I'm going to have this one sort of like stuck in your head, and then we can finish this one on Saturday morning if you like. All right. So here we go. So what I want to do is just coming up with a loop. A, B, C, D, A. So I'm going to loop like this. Like that. Okay. So what I'm doing over here is I'm just going to analyze my loop going clockwise. So all I'm doing over here is there's no junction here. So that's easy. So when there's no junction, what I'm going to do is this. I'm just going to keep analyzing my loop. Now I'm seeing a battery, and I'm going from here to here, right? My way of saying is I'm walking. So I'm walking here, I'm walking here. Now I hit the negative side of this one. I'm about to move to the positive side of this one. So I'm going uphill. I'm going higher in potential. So this one is exactly this case over here. So I'm going uphill. How much? 6 volts. So I'm saying I have 6 volts along with my walk. Keep going. Nothing. Keep walking. Nothing. Keep walking. Oh, now I'm hitting a resistor with a resistance 8 ohms. But right now, you are seeing that, hey, we assume, or we don't have to assume much, but let's say we say that the current flow is I that is flowing clockwise. So that means at 8 ohms, I'm having the current flow downward. So let me write on top of this one here. The current is flowing downward. So by walking, I'm going to walk in the same direction as the current flow. So I'm walking toward a lower potential. That is our case number 1 here, right? We're going from A to B in the same direction as the current. So over here, I'm walking in the same direction as the current flow. So I'm walking toward the lower potential. So it's going to be negative 8I. You guys read me? It's IR. Keep walking. Keep walking. Nothing. Now I'm hitting the positive terminal of my battery. I'm going toward the negative ends of this battery. So I'm going toward a lower potential. So delta V across this one is going to be negative 12 volt. With me? Keep walking. Nothing. And now I hit another R2. But R2 is now, we assume that the current is flowing clockwise. So I'm walking in the same direction as the current. So it means I'm going toward a lower potential. How much? Is going to be negative I times 10. Now keep walking. Now I'm back at A. I'm completing the loop. So the loop rule is saying positive 6 right here, minus 8I, minus 12, minus 10I must sum up equal to 0. And now I can solve for I, and I'm done.
Okay.
Isn't that cool? All right, just you guys should be able to look at this one. This is 6 volt, come from here. 8I, that's there. Negative 12, that's here. And that negative 10, that's right there. Those are the sum. See, that's how easy it is for you to apply loop rule. Okay. However, what we're going to do is now with these two rules, which we named this Kirchhoff's rule, we will be able to calculate currents flowing through this, believe it or not.
Okay.
All right. So what I'm going to show you right now is, all right, guys. So it might go over time just a little bit. Sorry about that, but I'm just going to lay down this whole thing. I'm just going to pause there. Okay. But at least I will have some sort of like something introduced to you today now, and then we can do it one more time next time on Saturday. Okay. So what I'm having over here is now, but John, it's so complex now. What we are going to do here. Okay. So what we're going to do is this. So you just recognize this one as we call it a multi-loop. This is a multi-loop circuit because there's like, okay, but I have loop here, I have another loop there, and I even have a big loop up there. See, that's multi-loops, right? So what we have over here is, okay, we have a lot of loop here, but we should be able to apply Kirchhoff's rule everywhere in this universe, pretty much. So what we're going to do is this. The easiest way for me that I'm gonna sort of like show you how it's done is I just try to look at the wire, the connector, the conducting wire that has no junction. That's my approach. Right here, I can see that there is a left wire over here. I can see that there is a middle wire over here. And I can see that I have a right side wire over here. See? So the portion that I highlighted, those are the one that doesn't have any junction. And these portions are combined at a single point over here and another point on the other end. So they're sharing a junction at A and B. Cool? Okay, so what I'm going to do is now next, you probably don't know that which direction that the current should flow. So don't worry, just crazily assume your current directions. Don't care. For example, if I follow the figure over here, I assume that the current is flowing upward on the yellow wire, and the current is flowing upward as well on the green wire, and the current flow downward in the blue wire, I3. Cool? All right. So don't worry about the correctness of the direction at this point because your final answer will direct what is the true direction of the current flow. Okay, cool. So with that, I can apply the junction rule right away. You guys look at junction A. At A, what happened, guys? There is I1 that's in, I2 is in, I3 is out. So the net current in must be equal to the net the current out from the Kirchhoff's junction rule. So I can say I1 plus I2 must be equal to I3. That's my first equation, guys.
Okay.
Cool. And now you start to be able to guess. Well, John, you have three unknowns. One equation is not enough. You need two more. And that's where the loop rule comes into play. Can you guess now? Pick a loop. I'm just kidding. Pick a loop. So what I'm going to show you, let's say I'm going to pick, it's going to look dirty a little bit, but that's what it is. I'm going to pick the A. Okay, let me call this. Oh, the A has already been used. So let me call M, N, O, P. Okay, so I'm going to pick loop. I'm going to look at the left loop. N, A, B, P, M. You guys with me? That's the left loop. So I'm going to start right here, M. And I'm going to just walk. Can you see? Walking clockwise. I'm going to loop back at M as well. So what I'm doing over here is I'm just going to collect delta V along the way. Okay? Follow me, guys. With me? I'm just walking. Now I'm phasing R1 with the current I1 in the same direction as my analysis. So I'm going downhill. So I'm saying I'm having a negative I1 R1. Keep walking, guys. Now I'm at A turn. Down along the blue wire. I'm phasing R2 with the I3. I'm walking in the same direction as the current. I'm going to a lower potential. It's going to be negative I3 R2. Keep going. Now I'm hitting my positive terminal of the battery. So that's mean going from positive to the negative terminal, I'm going downhill again. So I'm going to go negative E2. Keep going. Now I'm hit at B, turn. Now I'm seeing R1 with the current I1. I'm going in the same direction as the current, so I'm going downhill. So I'm going to get the negative I1 R1. Keep going. Now I'm hitting the negative terminal of my battery. So I'm going from negative to positive terminal. I'm going uphill, positive potential change, E1. Keep walking, hitting the M, complete the loop. This summation give you 0. You are done.
Okay.
This is equation number 2. That makes sense? It's like playing games here, right? And once again, it's not enough because you have 3 unknowns, I1, I2, I3. You only have 2 equations. So what do? Pick another loop, okay? Just to showcase that you have any freedom to pick any loop, any directions. So I'm going to pick loop. Let me do N, A, M, P, B, O, N. I'm going to do the outer loop here. And I'm going to go counterclockwise just to showcase it. It's fine. You can pick any loop you want. Okay. Starting from the upper right corner N. I mean, you can start anywhere you like as long as you close your loop. Guys, go. All right. Walking. I see R1 with the I2 walking in the same direction as the current. I'm going to a negative potential I2 R1. Keep walking. Nothing. I'm at A. Nothing. Now I'm hitting R1 with the I1 against me. So I'm going up the river. So positive I1 R1. Cool. Keep going. M. Nothing. Turn. I'm hitting the positive terminal. Going to the negative terminal is go lower. Keep going. I'm hitting I1 with the I'm hitting R1 with the I1 against me. So I'm going uphill. So I'm going a positive change in your in our potential difference. It's going to be positive change. Done. Keep going. Walking. Nothing. Now I'm at O. Turn. Now I'm facing another R1. But now my current is I2 in the same direction. So I'm going along with the flow downhill. So it's going to be negative I2 R1. Keep going. I'm hitting the negative terminal of E2, going to positive terminal. I'm going uphill, plus R2. I'm back at N. The sum must be 0. That's my third equation. And you are done. Yeah. Oh, not too bad. So that's it, guys. Kirchhoff's rule is right here. You apply junction rule, equation number 1, and loop rules for 2 more loops that you can pick out of your circuit. And once you have this, you end up with the 3 equations with 3 unknowns. You can solve for I1, I2, and I3, and you're done. Okay? All right. And as a final answers, if your I that you solve from this system of equations give you a negative value, don't worry. That means your assumed direction of the current is just opposite to your answer. That's all. For example, if I got I3 to be like example, negative 1. So it means the real current is actually flowing upward instead of downward. That's what it is. Okay, sounds good, guys? All right, so I think I'm going to stop here. So next time, I'm going to show you more, maybe 1 or 2 more of this so you guys can practice. And this will show up in the final exam for sure, like at least 1 problem here. Okay, and we're going to have a chance to apply this just a little bit more to close the whole course here next time, last lecture of ours. Sounds good, guys? Okay, and that is it for today. And I will see you guys on Saturday morning if you can make it. If not, just catch up on the YouTube playlist. Yeah. Okay, bye-bye. Take care.